Hi, and welcome to another lesson in the physics video series. Today we're going to be exploring the inelastic collision problem and the conservation of momentum. The conservation of momentum states that the momentum in a system before a collision is equal to the momentum in a system after a collision. In order to do this, we need to employ equation 13, P before equals P after, to account for all the individual momentum in each of the bodies that will be colliding. Alright, let's get started. What we have in front of us is a simple system of two masses, mass 1 and mass 2. And they are divided in this diagram by this line. On the left side of the line, mass 1 and mass 2 are in a condition before a collision, and on the right side of this line, mass 1 and mass 2 are in a new condition after a collision. And what are the conditions before and after? In this particular case, we have mass 1 approaching mass 2. Mass 1 has a speed v1, 10 meters per second. Mass 1 approaches mass 2. Mass 2 is at rest. So before they collide, mass 2 is like a car waiting at the red light and is at rest, and it gets hit from behind as mass 1 crashes into it. In this particular problem, in the after scenario, we are going to have a collision where the two cars lock together. This makes it an inelastic collision, and we're going to explain why it is called inelastic. At the moment of collision, mass 1 hits mass 2. Mass 2, which was at rest, now suddenly gains some momentum from the car that hit it, and it also gains a speed. Since the two cars lock together, v1 prime, that's the speed after the collision, and v2 prime are the same. Since v1 prime and v2 prime are the same, we call that v final. So this system of two masses, which is now locked together, moves away at the same final speed, where each mass, m1 and m2, move away together at v1 prime equaling v2 prime. Now let's derive an expression for the final speed of the group after the collision. So we have two individual masses before the collision, and we have the two masses locked together after the collision. Let's determine the final speed of the group based on the conservation of momentum. In order to determine the final speed of the group after the collision, we first must list the momenta for each one of the masses before and after the collision. So let's take a look at this line right here. The first mass and its speed is m1 times v1. That is the momentum of the first car before the collision. We're going to add that to the momentum of the second car before the collision, m2 times v2. Now at the moment, don't worry about this being canceled out to 0. We'll deal with that in the next line. Equals the momentum after the collision. So we have the same mass 1, but it has a speed v1 prime after the collision. And plus, we have the same mass 2, and it has a speed v2 prime after the collision. So before any cancellations, each mass gets its own momentum expression. m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. Now, let's apply the conditions for this particular collision problem. We know that the second mass was at rest, and if it was at rest, its v2 was 0, which makes this term drop out of the left side of this equation. We also know that after the collision, both masses moved away together at the same speed, making v1 prime equal to v2 prime. And wherever I see a v1 prime and a v2 prime, I can replace them with the common term vf. And here I have it, m1 vf plus m2 vf. Then, on the next line, I carry down and factor out. m1 v1 equals m1 plus m2 vf. So I factored out the common term of vf. Now that I have the term I want, vf, all I have to do is divide and separate terms so I can isolate vf by itself. vf equals m1 v1 divided by the parenthesis m1 plus m2. And here it is down here. Let me take a moment to explain to you why I've grouped the masses separately from the v1. Even though it is perfectly acceptable that I can have the v1 right up here next to the m1, m1 v1 divided by m1 plus m2, I've chosen to regroup the masses like this. bracket, m1 divided by m1 plus m2, bracket. This creates a ratio. So whatever the ratio of the masses are, that will give us a fraction proportion of the original speed. The final velocity of the group after the collision, when they stick together, is always going to be equal to the fraction of the original speed. Let's take a look at some examples of this, and it'll become clear in just a moment. Let's calculate the final speed of the two masses locked together after the collision when the masses are equal. m1 equals m2. So if m1 equals m2, and I go back to my original expression, wherever I see an m2, I'm going to replace it with an m1. And that's what I've done here. m1 divided by m1 plus another m1. However, m1 plus m1 is 2. So I have 1 m1 over 2 m1, canceling the m1s, leaves me with a fraction of 1/2. So what happens here is the final speed of the two collided masses is equal to half of the original speed of the first mass. Let's take a look at the simulation. Here we have the red car, mass 1 kilogram, and the blue car, mass 1 kilogram. We're going to set the initial velocity of the first car to 10 meters per second. We're going to set the initial velocity of the blue car to 0 meters per second. We're going to have an inelastic collision where they lock together. Let's run the simulation. And there it is. Both move off together at 5 meters per second each. In the diagram, we see that if m1 was moving at 10 meters per second when it hit m2, which was at rest, according to the formula, the final speed of the group should be half of v1. So in the case of equal masses, we have v final equals 1/2 of the original impact speed of v1. 1/2 of 10 meters per second equals 5 meters per second. So if mass 1 moving at 10 meters per second hits equal mass 2 at 0 meters per second, they move off together at exactly half of the impact speed m1, which was 10 meters per second. The fast car m1 moving at 10 meters per second gave its momentum to the stopped car m2, which had no speed. So in the final outcome, m1 slowed down to 5 meters per second, but m2 sped up to 5 meters per second. Where did m2 get its speed from? It got it from the momentum of m1. But what if the masses were unequal? What if m1 was twice as heavy as m2? That's a situation where a heavy car hits a lighter car. Let's look at the simulation one more time. This time we'll make the red car 2 kilograms, leaving the blue car at 1 kilogram. We will still have the initial velocity of the red car being 10 meters per second, and the blue car will be at rest. Let's run the simulation. And there you have it. They lock together and they both move off at 6.7 meters per second. So I go to the original formula, Vf equals m1 over m1 plus m2 as a fraction of v1. V final equals 2m2 over 2m2 plus m2 times the original speed of v1. That gives you a fraction of 2/3. So the final speed of the group after collision when they lock together is 2/3 of the original impact speed of mass 1. V final equals 2/3 of 10 meters per second, which means that the group moves together at 6.7 meters per second. Recall the results of the simulation. Both cars locked together and moved away at 6.7 meters per second. You can see that the heavy car kept going. It didn't lose much of its speed. And the lighter car gained a lot of speed. It had no speed when it was impacted, and then it had 6.7 meters per second. But what if we switch the scenario, and instead of a heavy car hitting a light car, what if a light car slams into the back of a heavy car? So the heavy car or truck is sitting at the red light, and a small car hits into it from behind. Let's take a look at the simulation once again. Now the red car is 1 kilogram and the blue car is 2 kilograms. This is light hitting into heavy. The red car will be moving at 10 meters per second and the blue car will be at rest. Let's run the simulation. And there you have it. The two cars lock together and move away at 3.3 meters per second each. So we take the original expression VF equals M1 over M1 plus M2 as a fraction of V1, and we put this ratio in. 2M1 equals M2. M1 divided by M1 plus, and then this place right here, we put a 2M1. And we add this together, we get 1M1 over 3M1, canceling M1, you get 1/3 V1. So what this means is that the final speed after the collision, when the two cars lock together, will be 1/3 of the original impact speed of mass 1 against mass 2. VF equals 1/3 of 10 meters per second, which is equal to 3.3 meters per second. Let's recall that the results of the last inelastic collision, light hitting heavy with a speed of 10 meters per second hitting a car at rest, resulted in 1/3 of the original speed. 3.33 meters per second was the combined velocity of the two cars moving together. It's a very interesting conclusion right here. And let's compare heavy hitting light to light hitting heavy. What we can observe is something that is intuitively understood about momentum. If a heavy object slams into a light object, the heavy object hardly slows down and it keeps going with much of its original speed. And that's what we see here in the heavy hits light condition. However, if a light object slams into a heavier object, most often, especially if the ratio is high enough, the light object does not cause the heavy object to move very much. And in this case, we can see that very clearly just with a 2-to-1 ratio. When the light object hits the heavy object, the whole group moves away at 1/3 of the original impact speed. Let's take a look at one last example of a 3-to-1 mass ratio. If we have a 3-to-1 mass ratio, and if we have a truck 3 times heavier than a car and it slams into a light car, let's take a look at what the final impact velocity will be. 3m2 over 3m2 plus m2 equals 3/4 of the original speed. If it's the other way around, and if a light car 3 times lighter than, say, the truck hits into the back of it, m1 over m1 plus 3m1 equals 1/4 of the original speed. So let's look at these examples of 3-to-1. The very heavy truck slams into the back of the car at rest. The car at rest gains from 0 speed to 7.5 meters per second. It jumps up speed, whereas the truck slows down from its original 10 meters per second down to 7.5 meters per second. So it gave some of its momentum to the lighter car, which is now moving at the same speed with it. Let's take a look at how this works in the simulation. Here I have placed 3 kilograms on the red car, which will be moving at 10 meters per second and will strike the blue car, which is 1 kilogram, at rest. Let's run the simulation. And there you could see that the heavy car keeps pushing through and slows down somewhat, while the blue car, which was 3 times lighter, gained a lot of speed from the momentum imparted to it by the impact of the heavier vehicle. However, in the opposite situation, if the truck was at the red light and a much smaller car from behind crashed into it, the two of them would only move together at 2.5 meters per second. So the car had an original speed of 10 meters per second, but after crashing into the back of the truck, it gave most of its momentum to the truck and lost most of its speed in the process. Let's take a look at this in the simulation. Here we have a very light car crashing into the back of a truck. We're making the mass of the red car 1 kilogram and the mass of the blue truck 3 kilograms. The impact velocity will be 10 meters per second and the blue truck will be at rest. Let's run the simulation. And there you can see that they lock together and they move away at 2.5 meters per second. So in conclusion, momentum applied to an inelastic collision problem will help you determine the final speed of the group after the collision by tabulating the individual momenta of each of the cars before and after the collision. After all is said and done, you can see that the final speed of the group is always equal to a mass ratio of the impact speed. There are other variations to the two-body collision problem. They do not have to lock together. They can bounce off each other, and the masses are not restrained to be moving in one direction. They can be moving left or right, and they don't have to have a 0 speed. We're going to take a look at some of those problems in the next videos. I hope you enjoyed this video, and I thank you for watching. I'll see you in the next video.